Your internet connection is a single strand of glass, thinner than a human hair. And right now, it's carrying thousands of conversations, video streams, and downloads simultaneously, all as light. How does it know which light is yours? Like, seriously, if 1,000 people are sending data through the same fiber optic cable at the exact same time, how does your computer get your Netflix stream and not someone else's bank transaction? How does the light know where to go? Is each person getting their own separate beam? Are the signals somehow labeled? Can light even be labeled? And here's what makes it weirder. The cable is just glass. There's no copper wire splitting into branches, no physical divisions, just one continuous thread of glass with light bouncing through it. So how is anything staying separate? Okay, so the simple answer is the light pulses are addressed. Like each burst of light has a little digital label that says, "This goes to apartment 4B," and the system just reads it. Except, no, that's not how it works at all. Because light doesn't carry labels. Light is just light. You can't write an address on a photon. So what's actually happening? The data isn't just light, it's packets. Think of it like this. Your computer doesn't send one continuous stream of light. It chops everything into tiny chunks, packets, and each packet is like a digital envelope. And on that envelope, an address. Your IP address, the destination IP address, routing info, and the actual data inside. So when thousands of computers are sending light through the same fiber, they're really sending thousands of these tiny addressed packets, all mixed together, all bouncing through the glass at once. And at the other end, a router reads the addresses and sorts them. It's basically a post office for light. Okay, but here's the weird part. If all this light is traveling through the same piece of glass, how does it not just blend together into nonsense? Like, imagine 1,000 people all shouting into the same tunnel at once. You just hear chaos. But fiber optic cables don't get chaotic. They stay clean. Why? Two reasons, and they're both kind of genius. First, different colors. Fiber optic systems use wavelength division multiplexing, which is a fancy way of saying we send different data streams on different colors of light. Red light carries one conversation, blue light carries another, infrared carries a third. They're all traveling through the same glass fiber, but they don't interfere with each other because they're literally different wavelengths. It's like having 100 radio stations all broadcasting at once. They don't collide because they're on different channels. Your radio just tunes into the one you want. Same deal here. The receiver filters for specific wavelengths and ignores the rest. So a single strand of fiber can carry dozens, sometimes hundreds, of separate data streams just by splitting them across the color spectrum. But that's not all, because even within a single wavelength, you can still fit multiple users. How? Time slots. Imagine you and 10 other people all need to talk through the same walkie-talkie. You can't all talk at once, so you take turns. Person 1 talks for 1 millisecond. Person 2 talks for the next millisecond. Person 3, person 4, and so on. You cycle through so fast that it feels like everyone's talking simultaneously, but really you're just taking turns at lightning speed. That's time division multiplexing, and fiber systems do this constantly. Your data gets a tiny time slot, my data gets the next slot, someone else's data gets the slot after that. So now you've got multiple wavelengths, each carrying multiple time-slotted data streams, all bouncing through one piece of glass. And somehow it all stays organized. Which brings us to the thing that makes fiber optic cables actually work in the first place: total internal reflection. So light is traveling through this glass fiber, but glass is transparent. Light passes through glass. So why doesn't the light just leak out the sides? Because the fiber is built in layers. The core, the center where the light travels, is made of glass with a high refractive index. The outer layer, the cladding, is glass with a lower refractive index. And when light tries to escape from the high index core into the low index cladding, it hits this boundary and just bounces back every single time. It's like a perfect mirror built into the structure of the glass itself. So the light doesn't travel in a straight line. It bounces over and over, zigzagging down the fiber at nearly the speed of light, trapped inside by physics, which is how a signal can travel hundreds of kilometers through a cable thinner than a hair without losing itself. But okay, here's the last piece. If light is traveling down the fiber in one direction, how do you send data back? Your computer isn't just downloading, it's uploading too. So how does two-way communication work in a single strand of glass? Two ways. Option 1, use different wavelengths for upstream and downstream. Your download comes on one color, your upload goes out on another. Same fiber, both directions, no collision. Option 2, use two fibers, one for sending, one for receiving. Most systems do a mix of both. And in shared networks, like the fiber system that connects your neighborhood, it gets even weirder. Your internet provider doesn't run a dedicated fiber to every single house. Instead, they run one fiber to your neighborhood, then split it. And when data comes downstream, it's broadcast to everyone. Every house on that split gets every packet. But your modem only listens for packets addressed to you. Everything else, ignored. It's like everyone's mail gets dumped in the lobby, but you only pick up the envelopes with your name on them. Upstream is trickier, because if everyone tried to send data at once, it'd collide. So the system assigns time slots. Your modem gets permission to transmit during its slot. My modem waits for its slot, all coordinated in microseconds. And that's how a single hair-thin piece of glass carries the entire internet to your house. Addressed packets, wavelength multiplexing, time slots, total internal reflection. Light that knows exactly where it's going because we taught it how to take turns. Which is honestly more polite than most humans on the internet.